Okay, this is MA 259, section 5.2, number 5. Once again, my plan here is to actually work out the problem. I will ask you to do a similar problem, scan it, or take a picture with your cell phone and turn it in via Blackboard. So the first thing is I have the system of differential equations where I have the first equation and the second equation. What I've done is written those systems in a matrix form where I have the vector x prime equals this A matrix 6 minus 7, that comes from 6 minus 7, 1 minus 2, 1 minus 2, and then times this x1, x2 vector. So my goal then is to define the determinant of the matrix A minus lambda I and set that equal to 0. So I have 6 minus lambda minus 7, 1, and then minus 2 minus lambda. So 6 minus lambda, negative 7, 1, minus 2 minus lambda. Find the determinant and set that equal to 0. So the determinant is 6 minus lambda times negative 2 minus lambda. 6 minus lambda times negative 2 minus lambda minus 1 times negative 7. 1 times negative 7. Then I set that equal to 0. I work out the algebra and simplify, and I get lambda squared minus 4 lambda minus 5 equals 0. I factored, and I get lambda equals 5 or lambda equals negative 1. I call this now lambda 1 equals negative lambda. I have the situation of the distinct real roots of negative 1 and 5. So I'm going to do 7 and then minus 7, 1, negative 1. And where does this come from? Well, I do A minus lambda I, and so I get 6 minus negative 1, negative 7, 1, negative 2 minus negative 1. So I have 7, negative 7, 1, and minus 1. A minus lambda I with lambda equal to negative 1 times the eigenvector v1, v2, and that's equal to the 0 vector. I take the A matrix and I put it in reduced row echelon form, and I get 1 minus 1, and that really stands for v1 minus v2 equals 0. v1 minus v2 equals 0, v1 minus v2 equals 0, and v2 being a free variable that I call c. When I solve this and I put this minus v2 over on the other side of the equation, I get v1 equals v2, and v2 is equal to c. So I choose 1, 1 because that'll work. I have 1, 1, c, c. When I do that, I get this x1 of t is equal to e to the minus lambda. So e to the minus lambda t is e to the minus t times my associated eigenvector, 1, 1. I do the same thing for lambda equals 2, where lambda is equal to 5. So my second eigenvalue equal to 5. I plug that into A minus lambda I, and I get 1 minus 7, 1 minus 7, times this associated eigenvector, v1, v2, and set that equal to 0, the 0 vector. And I get 1 minus 7, 1 minus 7, and I put that in reduced row echelon form, and I get 1 minus 7 with 0, 0. So what that means is I have v1 minus 7v2 equals 0, and v2 is my free variable. I take this minus 7v2 and I move it to the other side of the equation, and I get v1 equals positive 7v2, and v2 equals c. So I have 7 times c equal, v1 equals 7 times c, and v2 equals c. So I have v1 equals 7c, v2 equals c. and I chose C to be equal to 1. I could choose other numbers, but I chose 1, and then I get eigenvector 2 is equal to 7, 1. And so my x2 vector is equal to e to the lambda t, or e to the 5t, times 7, 1. I combine those two together and get x of t equals e to the minus t times 1, 1 vector times some c1 plus e to the 5t times 7, 1 vector times some c2.